One of the connections or applications of higher order derivatives that we've seen before was the construction of higher and higher accuracy approximations to complicated functions at a point. And we called those earlier Taylor approximations. The Taylor polynomials can also be generated when we're talking about functions of several variables. As we'll see, the formula gets more complicated in a hurry compared to the single variable calculus. So we're going to limit ourselves to quadratic approximations. But we'll see that the structure is a pretty clear generalization of what we've seen already for linear approximations, and see how it ties back to the Taylor series for polynomials when we only had one variable. So just a brief reminder of what we've seen earlier. We can talk about linear approximations, which is our function, and then we add an x derivative times delta x and a y derivative times delta y. That is one way we construct a linear approximation. And it can be called any number of things. Sometimes we call it the local linearization, or near a point or at a point. It's an approximation that's valid nearby. We can also call that the equation of the tangent plane. So if we pick a point on a surface and draw it as a surface in 3D, this would be the formula for the plane that just touches at the one point we picked and has the same slopes as the surface itself. And new terminology, linear functions are polynomials. They're just really simple polynomials. They're polynomials of degree 1, and we would call this a Taylor polynomial of degree 1 centered at AB. The idea being maybe we can generate other polynomials also centered at AB that might be higher order, and in particular we're going to look at quadratics. So what we might want to do, again thinking of a surface, is we talked about making a tangent plane to that surface, but that's a pretty crude approximation to something that has some curvature. It might be better to say, well, what if we could fit a parabolic bowl shape to that surface, or something along those lines? That would give a much better approximation nearby than the tangent plane would. Tangent plane has no curvature. We can have slopes match and curvature match if we build a quadratic approximation. So let's see how we might go about doing that. I think the natural approach to this is to generalize from what we saw before and say our function can be approximated by, well, remember how we built quadratics back in the first term. F of AB, the quadratic approximations we built in the first term were actually just an extension of the linear approximation. So in fact, everything from the linear approximation makes it into this quadratic approximation. So that's our earlier linear approximation. And all we do is start adding to that. So we're going to add a bunch of stuff. Now what are we going to add? Well, if we're going to have a quadratic, pardon me, if we're going to have a quadratic approximation, we have to have something about the curvature. And what we'd like to have is the curvature match. So having the same concavity in our surface as in our function, or as in our approximation, it shouldn't be a huge surprise to see a term like this, which is what we saw in the earlier approximations in the first term. We can also talk about an approximation in the y direction, though, because this is only the x concavity. What about the y concavity going in this direction? Well, the same thing would apply there. And let me highlight some things here. I'm going to write them in color to make it more obvious. When we have the second derivatives, we multiply it by the quadratic terms. This is how we get a quadratic approximation. And again, because the quadratics are something about curvature and the second derivative is something about curvature, it kind of makes sense that these two go together. And last but not least, though, we also have the mixed partial derivative. Now, if you think of these two terms as x minus a twice, if we have the mixed partial, it's not obvious that this is true, but it's not hard to show that to get a quadratic approximation that has all the same second derivative information as your complicated function, you need to have the xx, the yy, and the mixed partial derivatives all represented in your approximation. Now, there's one last thing we need to include. If you think back to the first term, there was a half factor that showed up here, and we also need that for the y. Again, you think if you differentiate this, the 2 will come down and it'll cancel. It's important to note that this term here won't have that 1/2 factor, and it comes down to technicalities. If we differentiate this once with respect to x and once with respect to y, we don't get any 2 popping out. So our function and the xy derivative would end up looking identical without any constant appearing here. Whereas when we differentiate this term twice with respect to x, there's a 2 that pops out. We don't want to have that 2. We just want to be left with the x second derivative. So another way to look at it is this has a 2, that has a 2, that has a 2. So does that. No 2's, no 2's. That's another way to memorize it anyway. So that's how we can construct our approximation as a formula. And as I say, the derivation of these coefficients is pretty tedious, but it is straightforward. It's just matching your function's second derivatives with this approximation second derivatives and seeing what constants you need to slide in to make them equal. Let's do an example here, simple calculation of a Taylor polynomial of second degree. Basically, this is a laundry list type question. You've got the Taylor polynomial and you're trying to approximate some function. Again, this is a complicated function. We're going to approximate at the point 0,1. What I usually do is just write out my laundry list of functions and its derivatives. That's our function. Then we have our first order derivatives, so fx. I'm just going to write fx here. The x derivative of that is minus sine of 3x times 3 times y squared. Fy would be y derivative, cos is the constant then, cos of 3x is constant, times 2y. Those are our 2 first order partials. And then we can go to the second order partials. Let's go to the xx. So we differentiate this with respect to x. We're going to get negative cos of 3x times another 3, so we're going to have times 9, and the y squared is a constant. Second order partial with respect to y, we're going to differentiate this with respect to y. Cos 3x is a constant, and the derivative of y is 1. And last but not least, our mixed partial derivative. Either way you'd like to do it, I think this one's simpler. Let's take the x derivative of this. We're going to get minus sine of 3x times 3 times 2y. What do we do next? Well, we put it at the point 0,1. Let's do a line here. At the point 0,1, this value, let's remember cos of 0, I'll stop our head here. Cos of 0, always 1. And sine of 0 is going to come into play too. Sine of 0 is 0. So we got cos of 0 is 1 times 1 squared, that's 1. Sine of 0, 0. Everything else doesn't matter. Cos of 0 is 1 times 2, that's 2. Cos of 0 times 9 times 1 and negative, we get negative 9. Cos of 0 is 1 times 2 is 2. Sine of 0 is 0 times whatever, doesn't matter. So the Taylor approximation, sometimes called P2 of x of y, so quadratic, we often use the symbol P2 for polynomial of degree 2, or we could write it P2 of xy equals that, or f of xy is approximately equal to this function that we're going to build here. So it's the function value plus 0 times x minus, what are a and b here? That's our a, that's our b, the points at which we are considering the approximation. And then we have the y derivative, that's 2 times y minus 1, plus all the second derivative stuff. Minus 9, x minus 0 squared, and we don't forget the over 2, plus 2, y minus 1 all squared, and we don't forget, oh yeah, that one's divided by 2, and then we get the mixed partial derivative down here, which is 0, x minus 0, y minus 1. So that's applying our formula from the last page. Might help to have it in front of you while you do it. constant term, 2 linear terms with the x and y derivatives, 2 quadratic terms with the double x, double y, and then the mixed partial derivative term. Of course, we should simplify this. This is just a nice clear connection between the formula that we had before and this particular example. But at the end of the day, we're going to get 1 plus 2y minus 1 minus 9 halves x squared plus y minus 1 squared and plus 0. So that would be a quadratic. We notice it is quadratic, quick check, with constants out front of the linear and quadratic terms, and this would be a good approximation to this much more complex function, cos of 3x times y squared, around the point 0, 1. Quadratic sometimes easier to deal with than something as complicated as this trig combined with the polynomial. For us in this class, the Taylor polynomial is essentially something that you memorize and then apply in a particular problem. There are some connections to what we're going to see next in terms of optimization, but they're long to derive, not particularly, most students don't find it insightful to think about a lot of the stuff that we talk about there. So for now, I would treat the Taylor polynomials in terms of filing in your calculus ideas as simply something that's a generalization of the tangent plane. There's a formula for it. The formula has a nice structure, and it's an approximation to a complex function. And leave it at that for now.